Hey y'all, today we're going to look at our last set of interparticle forces, and those are going to be the ones which involve ions. We're going to look at ion-ion interactions, ion-dipole interactions, and we're going to look at more specifically how ionic compounds go into solution in water. Let's go ahead and start with ion-ion interactions though. Ion-ion interactions are often known as ionic bonds, and ionic bonds in the solid form what's called a crystal lattice. Now, the crystal lattice is a regular repeating pattern of these ions, and inside of the crystal lattice, there are both attractive and repulsive forces. So the actual structure of the lattice itself maximizes the attraction between ions and minimizes the repulsion between ions. For that reason, different compounds will have different lattice geometries, different lattice structures. You don't need to know the actual geometries or structures of the lattices themselves, but you do need to understand that the overall structure of a lattice maximizes the attraction, minimizes the repulsion. And that's the case in pretty much any bond. We talked about the same thing in a covalent bond, right? Where the interparticle distance or the internuclear distance maximize the attraction, but minimize the repulsion. So we're going to see the same kind of characteristics in an ionic bond. The big difference in ionic bonds is the role which Coulomb's law plays. So let's take a look at that real quick. Coulomb's law, if you remember, is the charge over the distance. Now, in an ionic bond, the charge is actually pretty straightforward. It's the charge of the ions involved. So a sodium ion would have a +1 charge, where a chloride ion would have a -1 charge. Now, the distance in ionic bond is dictated based on the size of the ions themselves. So a larger ion versus a smaller ion. Larger ions would have greater distance between, right, versus a smaller ion which would have a lesser distance between. The greater the distance, the less the force of interaction is overall. The smaller the distance, the greater the force of interaction is overall. So in general, our rule of thumb for crystal lattice energy, which would be the energy of an ionic bond, the smaller the ions and the more charged the ions, the stronger the lattice energy, or the stronger the energy of the ionic bond. Let's take a look at 3 examples here. Here I have sodium iodide, calcium iodide, and magnesium iodide with their ionic lattice energies listed. Now, if we take a look, the sodium iodide, the calcium iodide, and the magnesium iodide have 2 variables. First of all, the sodium is a +1 charge, whereas the calcium and magnesium are +2. Secondly, sodium, calcium, and magnesium are all different sizes. Now, we can't compare both at once. So what we're going to do first is we're going to compare based off of charge. Okay. So the sodium iodide is going to be a +1 charge and a -1 charge, compared to a +2 and -2 charge. So the +2 and -2 charges, you can see, and again, the -2 being 2 iodide ions, you can see that there's a much stronger force of attraction. The lattice energy is much greater in the calcium and magnesium iodide than it is in the sodium iodide. So that's an effective charge. Now, the effective distance we can see between the calcium iodide and the magnesium iodide. The calcium iodide is going to be a bigger ion. Well, the calcium itself is a bigger ion, at least. Magnesium is a smaller ion. So what we can see here is that the magnesium iodide has a stronger lattice energy because magnesium is a smaller ion than the calcium is. Okay, so the calcium is going to be bigger, the denominator gets larger, force of attraction becomes less. So in this case, we can compare the 3 different ions and predict relative lattice energies. Okay. Again, it's not perfect because in some cases the actual geometry of the lattice will play a role, but for the purposes of this class, we're not going to look into that. We're just focusing on the Coulomb's law element, which is charge and distance. The next thing we're going to look at are ion-dipole interactions. Now, ion-dipole interactions are just as the name suggests. It's the interaction between a positively charged ion and a negative dipole, or a negatively charged ion and a positive dipole. Now, these ion-dipole interactions are really mostly relevant when we're talking about aqueous solutions. Water is a polar molecule. So anything that dissolves in water, any ionic compound that dissolves in water, is going to experience ion-dipole interactions with water molecules. Be aware, in water, the oxygen is partially negatively charged at least, and the hydrogen is partially positively charged. So when we're looking at dissolving in solution any ionic compound, the oxygen atoms are going to surround the negative or the positive ion, the cation, whereas the hydrogen atoms are going to surround the anion, the negative ion. So in sodium chloride, if we take a look at the particle representation of sodium chloride in solution, you'll see that the sodium ions are all surrounded or hydrated by the water with the oxygen atom facing the sodium ion. And the chloride ions are going to be hydrated or surrounded by the water, but where the hydrogen atom is facing the chloride ion. Now, it's really important that you realize that this interaction is more complicated than it looks. All right, the number of atoms or the number of molecules of water around each ion differ, and the relative interactions differ. And this actually plays a big role in the thermodynamics of dissolving that we talked about back in thermochemistry. We talked about how the three processes of dissolving, one was breaking the water molecules' hydrogen bond forces, one was breaking the energy of the crystal lattice within the solid ionic compound, and one was the forming of ion-dipole interactions between the ions in the water. That's called the hydration process. So this whole process of dissolving is more complicated than it might initially appear, but we can at least represent it appropriately if you know how to draw the particles properly. Oftentimes you're going to be given a number of particles, say like, hey, you need to draw 2 cations and 2 anions and a minimum of 6 water molecules, and they'll kind of give you some guidance in terms of how to draw it. But the reality is you need to make sure you get the representations correct in order to assess who's being attracted to who. Remember, ion-dipole interactions are relatively strong because ions have full charges. And the more polar the dipole would be, so the stronger that dipole moment is, the greater the force of attraction will be between the dipole and the ion of opposite charge. So that wraps up today's video. Let's do a quick recap. Today we talked about how ion-ion interactions are also known as the crystal lattice in their solid form, and we talked about lattice energy varying based off of Coulomb's law. Remember, the greater the charge of the ions involved and the lesser the size of the ions involved, the greater the lattice energy will be. That means it's going to be harder to tear apart that ionic compound. It means greater melting point. In terms of ion-dipole forces, we also talked about how those ion-dipole forces are very relevant in making solutions, especially aqueous solutions, where water is a polar molecule and ions have charge. Remember, when we're drawing these in particle diagrams, you need to make sure you get the orientation of the ions to the water correct, where the positive ion is attracted to the negative dipole of the water, and the negative ion is attracted to the positive dipole of the water. Make sure when you're drawing this, you're paying very close attention to numbers of ions and molecules you're representing, because that's going to play a big role also in terms of getting the overall answer correct. So I hope you enjoyed this video, and I will see you in the next one.